Hello, my name is Jose Antonio Fonseca, and this is my argumentative exam for my design of cyber-physical systems class. So let's begin with Industry 2.0. Before transitioning to Industry 4.0, our automotive workplace operated under a traditional Industry 2.0 framework, characterized by mechanized processes, manual labor, and isolated production systems. In this environment, several critical areas of opportunity were identified through a detailed diagnostic. In the Industry 2.0, automotive station ergonomic risks were widespread and largely unaddressed. Workers regularly operated in non-neutral postures, bending and twisting due to fixed height work surfaces. Apart, the power zone for lifting was ignored, with materials stored too high or low, increasing lower back strain. In the Industry 2.0 automotive workstation, there was also a clear mismatch between takt times and cycle times, 10 minutes and 12 minutes respectively. This imbalance caused production delays, bottlenecks, and worker fatigue. The absence of standard procedures, ergonomic design, and real-time monitoring led to inconsistent performance, increased errors, and reduced productivity, making it difficult to meet demand efficiently. In the Industry 2.0 plant, downtimes averaged 15% per shift due to equipment failures, manual part handling, and lack of preventive maintenance. With no real-time monitoring or diagnostics, issues were only addressed after breakdowns. So poor logistics and coordination led to delays, idle time, and disconnected systems that lack predictive capability, making production unreliable and inefficient. So continuing with defective fraction, it reached 2.1%, mostly due to manual errors and lack of automatic validation. The effects were only caught during final inspections, leading to rework, delays, and quality issues. Poor training, physical fatigue, and absence of real-time feedback made quality inconsistent and reactive, underscoring the need of automated, traceable systems in Industry 4.0. The Industry 2.0 automotive workstation presented as well several compliance issues with the key STPS safety norms. Under NOM 001, electrical panels were often unavailable and lacked proper shut-off access, posing electrocution risks. In terms of NOM 006, the handling of hazardous substances lacked proper labeling, secure storage, and appropriate PPE. The psychosocial environment violated in NOM 035, with no structured breaks, high task repetition, and no challenge for reporting stress, raising long-term burnout concerns. Additionally, NOM 036 was clearly neglected, as workers frequently lift heavy parts and lack mechanical aids, increasing the risk of musculoskeletal disorders. While the system remained operational, it was fundamentally non-compliant and reactive, making it unsustainable in the long term and reinforcing the need for a shift into a regulation-aligned Industry 4.0 environment. In the Industry 4.0 transition, the automobile workstation was redesigned using cyber-physical systems that integrate industrial Internet of Things and digital twins. Sensors enable real-time monitoring of cycle times, torque, and equipment health, while digital twins simulate workflows and ergonomic risks before implementation. The system adjusts dynamically to reduce physical strain, prevent downtime, and optimize output, aligning with goals of productivity, safety, and sustainability. Though it requires upfront investment, long-term benefits in efficiency and compliance justify the change. In industry redesign, the human factor 4.0 was prioritized by integrating technologies that enhance worker safety, comfort, and performance. Cobots assist in repetitive tasks, improving posture and reducing injuries while removing human input. AR instructions project real-time guides, improving accuracy and reducing training time, though they may cause visual fatigue, but it can be assessed with lenses. Wearable ergonomic monitors track posture and stress, helping prevent strain through data-driven interventions. These tools create a more intelligent, responsive, and worker-centered environment. To implement the redesigned workstation, we integrate additional Industry 4.0 technologies beyond AR and Internet of Things. Collaborative robots assist with repetitive heavy tasks, as already mentioned, and we included big data analytics to process information from multiple sources to detect inefficiencies and optimize performance. Cloud-based systems store and manage this data securely, enabling remote supervision and system updates. Together, these tools transform the station into a flexible, intelligent, and human-centered environment, built for continuous improvement and operational excellence. The redesigned workstation integrates sustainability, worker well-being, and ethics. It complies with NOM 001, 006, 035, and 036, applying circular economy practices like component reuse and smart monitoring of hazardous substances. Ergonomic stations, better lighting, and wellness dashboards enhance safety and comfort. To address job shifts from automation, a human factor 4.0 training program upskills workers for supervisory and analytical roles. Transparent policies support inclusion and ethical implementation, making the system not only efficient, but also socially responsible and human-centered, as well as including it for the circular economy and focusing on end-of-life processes.